In this lesson, we're going to talk about the average rate of change. In the previous section, we were looking at linear functions where the rate of change was constant. Let's change things up and try to find an application of this slope idea when you don't have a constant rate of change. We previously discussed the example of the Olympics. Now let's look at the Olympics from the 1960s and the 1990s. What we're going to do is treat this kind of like it's a line, even if it's not a line, and calculate a rate of change for 1960 to 1968, as well as 1992 to 2000. And let's just see which one did better. For 1960 to 1968, we're looking at this data for the ending point and this data for the beginning point. Let's treat it like an x1, y1 and an x2, y2. So then we have that the slope that we would be talking about would be 213 minus 185 over 1968 minus 1960. That gives us 28 over 8, which is equal to 3.5, and just in the units you again have inches per year. Now for 1992 to 2000, we'll do something similar. We'll say 232 minus 228 over 2000 minus 1992. This time we get 4 over 8, which is 0.5 inches per year. Not the best change, but still, it's going up. Now just to point out something though, if you look at the data that was in this table, 232 in 2000 was actually less than the 233 in 1996. So this is sort of an averaging out, ignoring data in the middle and just looking at the trend from the beginning to the end. Now, second question was which one was better than during the period of 1900 to 1912? That was 2 inches per year in the last section. So in the 1960 to the 1968 year, that was faster than 1900 through 1912. Now let's note that we used exactly the same formula that we did for slope. So when we use that same formula, we just call this the average rate of change. The average rate of change, you might recall I called it f of x2 minus f of x1, but now I'm calling it f of b minus f of a. Same thing, over b minus a. This is a formula to definitely keep in your mind when you're looking at average rate of change. And it is the same as slope. This really is nothing more than y2 minus y1 over x2 minus x1. We just use a different formula. Now, when you're doing an average rate of change formula, you will always be given your A and your B. In this case, A is 1950 and B is 1970. And so the graph here is showing us the number of farms in the US in millions, and we want to look at the average rate of change between 1950 and 1970. Let's just take our best guess and try to estimate on this table. I'm going to say this number is about 5.4, and I'm just simply looking as what is the height of that point on this graph at the year 1950. And then for 1970, let's say this point is about 2.8. Remember, A is 1950, so this is f of a, and B was 1970, so this is f of b. The function value is nothing more than the y-coordinate associated with that x-coordinate, so we pull it from the point on the graph. Now let's use the formula. F of b minus f of a over b minus a. F of b is 2.8. F of a is 5.4. B was 1970, I'll just put 70. And A was 1950, and I'll just put 50. Doesn't really matter because we're going to get the same thing when we subtract. When we do this, we get negative 0.135. Now let's pay attention to the units here. It's the units of y over the units of x. Y is in millions of farms, and x is in years. So we're looking at millions of farms per year. Now I really don't like writing an answer like this. Would anyone take you seriously if you said 0.135 million farms? No. It would be much better to convert that to something a little bit more meaningful. So let's write it this way. The number of farms decreased by 135,000 farms each year. So it's much better to change the negative sign to the word decreased and to change this weird 0.135 million to the simpler answer of 135,000. Watch out for this on a quiz or test potentially. For the next example, we have a table for the data, whereas we had a graph for the previous one. We're looking at the industrial pollutant PCB, and the data in the table shows how the thickness of pelican eggshells is related to the concentration of PCB in parts per million. That's what this ppm stands for. If we want to find the average rate of change, we're going to let 87 be our A and 452 be our B. A is generally the smaller value and B is generally the larger value, but technically the formula will work if you switch them so long as you're consistent. So then if we go to apply our formula, f of B minus f of A, f of B is the 0.14 that is shown in the chart corresponding to the 452 that's our B, and then it's 0.44 at the 87 mark over 452 minus 87. This gives us negative 0.3 over 365. Now if you plug that in your calculator, you might get a really weird answer, so I'm just going to write down what the calculator might say. Negative 8.219 e minus 4. Doesn't really tell you that's a negative sign, but it actually is a negative sign on this 4. But the question is, what in the world does that mean? This is actually a little bit of scientific notation. What this means is we actually need to move the decimal point back 4 places. That gives us negative 0.0008219. And the units are strange, but it's the units of your output, which is in millimeters, per the input variable is parts per million. So millimeters per parts per million. Now it is a little bit small, but it grows over time. You can see how much it changed the pelican eggshell. The eggshell decreases in thickness by 0. That very, very small number for each part per million increase of PCB. Like I said, it seems small, but it makes a big difference as it grows. Here's a geometric way of looking at average rate of change. Remember, this is a slope, so the slope can be looked at as rise over run. If you consider the delta y and the delta x that we talked about, you're really just taking a curve and saying, let me isolate 2 points on this curve, and then draw the line that goes between them. So the slope of what we call a secant line here is the same as the average rate of change. Having that visualization can sometimes help us do problems very quickly. For this example, let's start off by finding the average rate of change using a formula this time. In this case, my A is x equals 1, and my B is x equals 4. When I'm doing problems like this, you can do it all at once, but I recommend just plugging the values into the function before you even go into the average rate of change formula. So let's say f of A. F of A, we have the square root of x as my function, so I have the square root of 1, which is 1. F of B, if I plug in 4, the square root of 4 is 2. And now I can plug that into the average rate of change formula. F of B was 2, F of A was 1, B was 4, and A was 1. That gives us 1/3 as the average rate of change. Now let's see if we can visualize this. Let's start off by doing a quick graph of the square root of x. It passes through 0, 0, 1, 1, 4, 2, and really just any other perfect square easy points on the graph. Here's the graph that passes through those 3 points. The average rate of change is the slope of the secant line that passes between x equals 1 and x equals 4. So if I were to draw that straight line as straight as I can get it, the slope of that line is actually the average rate of change. Now let's move on to C. Which is larger, the average rate of change between 1 and 4, or the average rate of change between 4 and 5? For 4 and 5, let's try to draw another straight line. So that slope is my 4 to 5 average rate of change. Now notice that the slope of the green line is clearly higher than the slope of the red line. Remember, the slope is the average rate of change, so that means that the average rate of change on 1 to 4 is higher. So a good way to word this is the average rate of change on 4 to 5 is smaller, since the corresponding slope is smaller. Now what is this telling us? If your slopes of these average rates of change are getting smaller, there's actually a neat graphical property you can pull off of this. Notice that this graph has this bending in it. If it were going straight, it would have started here and just kind of gone straight, but it was bending downward. And a way to view that bending downward is to see that these average rates of change are decreasing. So let's say this, and then we'll move on to talk about it in more detail. The function is bending downward. This property is what we call concave up and concave down. Concave up means that the rate of change, you can look at it as the average rate of change, is increasing during the interval. And if it's concave down, that rate of change is decreasing through the interval. So concave up is bending upward, and concave down is bending downward. Now this might be a little bit weird to look at in some of these pictures I have here. The first two are both concave up, but one is increasing and one is decreasing. The fact of the matter is that concave up and concave down are independent from increasing and decreasing. Same thing for concave down. But there is an easy test that given a graph you can figure out how it's concave up or concave down. Just draw in a few secant lines. Notice if I draw these in either place they're actually lying above the curve. So when your secant lines lie above the curve, it's concave up. Now if I do concave down and draw in some secant lines, notice that they lie below the curve. So when that happens, you can say that it's concave down. Let's use this idea to estimate the intervals on which a function is increasing and decreasing versus concave up and concave down. For increasing and decreasing, you can probably spot this very easily. You can see that it hits a place at 2 where it stops increasing and starts decreasing. And then at 6, it stops decreasing and starts increasing again. That should be easy to write down. So for A, it's increasing all the way up to 2. The way we should write that in interval notation is negative infinity to 2. Now increasing doesn't really happen at a single point, so oftentimes we will use parentheses whenever we close these off. But it's also increasing after 6, so let's put the rest of it as a union with 6 to infinity. And again, the union symbol in this case just as a way to join two intervals together. And then with that, the decreasing is between 2 and 6. Now for concave up and concave down, this is a little bit harder to spot. My tip to you is one that works great for me, but think about it as this is a road. It's a top-down view of a road that you're driving down. And as you're driving down that road, you're turning your steering wheel to the right when you're going around this curve. And then somewhere around here, you straighten out your steering wheel and start to turn it to the left to continue to go down that road. So in my mind, that tells me that at 4, approximately, is where this function seems to be switching in the direction that it's going. Let's draw in a few secant lines just to show that also. Notice that if we go across this thing, it is below the curve everywhere until we get to about 4, and then it switches to being above the curve when we draw in these secant lines. That's another reason why we've suddenly gone from concave down to concave up. So for B, concave up is happening where the secant lines are above, so that's going to be on 4 to infinity. And concave down was where the secant lines were below, so that can be negative infinity to 4. Now let's do a table example. Based on the table, you can look right at this and say, yeah, the function values are going up, the function's increasing. There's a really easy way to say that. We can say that the function is increasing simply because the numbers are rising. However, there's actually another explanation that you can use to say that this thing is increasing. Let's look at the differences here. For this first one, it goes up by 0.5, and then it goes up by 1, and then it goes up by 2.1, and then 3.8, 9.6, and 13.1. Now you'll notice those are rising too, but that actually means something else. This is what we'll call the first differences. And the rule is that it's increasing if the first differences are positive. And that's denoted by the blue numbers. Now, the question is this concave up or concave down? The way to tell is to actually look at these first differences. If these values are increasing, that's the idea of concave up. Because again, concave up means that the function has change increasing. So the way that I would probably write that is the first differences are rising. But again, there's another way to look at this. So another option I can do is I can actually calculate what's called the second differences. The second differences would be the difference in the first differences. So you see this goes up by 0.5, and then 1.1, 1.7, 5.8, and 3.5. Now notice these numbers are not consistently increasing, but they are consistently positive, and that's what we're looking for. The second differences are positive, and these are again labeled by the green numbers. These can be a little bit tricky, so we'll do one more example. In this one, let's just go ahead and say, yes, we can tell immediately, this one's increasing. The numbers are clearly rising. Now to figure out concave up or concave down, let's first calculate the first differences again. So we have a rise of 6, then 5, then 4, then 3, then 2. So all of these values are positive, which is not anything to do with the concave up or concave down. The fact that these first differences are positive is just another reason why this thing is increasing. However, notice that these values, the first differences, are decreasing. Remember, concave up means that the rate of change is increasing, and concave down means that the rate of change is decreasing. These blue numbers, these first differences, are basically the rate of change. The rate of change is decreasing. Therefore, it's concave down. And let's write down an explanation for this one. The first differences are decreasing, and again, those are the blue numbers. Now for the second one, let's calculate the second differences. This is where it's going to look different from the last problem. 6 to 5 is a -1, and 5 to 4 is a -1. 4 to 3 is a -1, and 3 to 2 is a -1. Remember, these are what we call the second differences, and the second differences are all negative. That is what's going on here. Since the second differences are negative, that's another reason why this is concave down. There's actually one more way that we could potentially explain this. If you really liked the problem with looking for concavity on a graph, you could actually plot these points and connect them with straight lines and get a feel for it being concave up or down that way. Let me draw a quick example for this table. Here's our graph, so let's plot our points as accurately as we can. We started off at the point 1, 1, and I have a scale of the 5 scale on the vertical axis. Then we have 2, 7, 3, 12, 4, 16, 5, 19, and 6, 21. Now let's just draw some straight lines through these. It's kind of hard to tell because I drew this on a plane that didn't have any grid marks, but you can see that this graph is actually bending downward. And because it's bending downward, that's yet a third reason for why this is concave down. Let's go back to average rate of change for a minute. We have a ball that's thrown in the air, and the height of the ball above the ground is given in this table. Let's find the average rate of change of the height of the ball during the first 3 seconds. This is one thing you want to be familiar with. When it says the first 3 seconds, that means A equals 0 and B equals 3. So if I'm using my formula, then with B being 3, f of B is 90. F of A was 0, so we have 0 over 3 minus 0. That gives me 30, and this would be in feet per second. Now it says, interpret your answer. The average speed of the ball was 30 feet per second during the first 3 seconds. Now why did I say speed? There was nothing about speed in here, it just wanted to know the average rate of change. Well, speed, or the word velocity, although there's a little bit more to that term, is distance over time. Feet is the units of distance, Seconds is a unit of time, so this is actually speed. Let's do this for the next one. If I plug into the formula this time, I'm looking at a equals 4 and b equals 6. So f of 6 would be 0. F of a is 4, so I get 80 over 6 minus 4. And I get negative 40 feet per second. Now the question is, why did the sign change? Well, take a look at these heights. From 0 to 3, the heights were rising, and then from 3 to 6, the heights were falling. So the speed, if you will, is negative. Now that doesn't make any sense to talk about speed being negative, but you can talk about a velocity being negative, and that means we're basically just having a direction. The negative represents the ball falling downward. The ball now has a negative velocity, meaning that it is falling this time. So this gives us a fundamental idea. The average velocity would be the change in distance over the change in time. So if you find the average rate of change for a function that gives position, then that average rate of change will be the average velocity. So I mentioned there's a difference between speed and velocity. Speed is just a measure. Speed is a number. Speed represents how fast something's going, but a velocity can be in any direction. Now, velocity actually does not have to be just positive or negative. You could use vectors to get a direction for the velocity as well. However, we'll just stick to one-dimensional, moving forward or backwards, up or down, something like that. Let's look at this example. Car is traveling away from home on a straight road, and its distance is given in the graph below. Now, I don't even have a y-axis scale. I don't know how far this is. But the question of whether the average velocity is greater during the first hour or the second hour? Remember, average velocity is an average rate of change. And geometrically, when we did average rate of change, we could draw a little secant line in. So let's do that. If I draw in the secant lines from 0 to 1 and from 1 to 2, you can clearly see that the slope of the first hour is much higher than the slope of the second hour. That means that the car is traveling faster in the first hour. Let me first write down the observation. The first observation was that the average speeds are represented by the slopes of the two segments, again because the slopes represent the average rate of change. And now let's just write down our result. Since the first hour has a higher slope, the car was traveling faster during that first hour.